For today's lesson, we're going to talk about Newton's first law of motion. So Isaac Newton, which the unit for force is named after, the Newton, we discussed that in last class. Well, he came up with three laws to describe how forces affect the motion of an object. So for today's lesson, we're going to talk about the first law of motion. So let's kind of review what we talked about last class with net force. So remember, net force is the total of all forces acting on an object. So if we have a race car here, which experiences 100 newtons of drag and 120 newtons of thrust, what would be our net force, or the difference? And so we would just subtract them. So 100 minus 120 gives us a difference of 20 newtons, and it's going to move left, and the car should start to speed up because we're experiencing a net force of 20 newtons. So answer that first question on your worksheet. What causes a change in the speed or direction? So the answer is a net force. So we have to have a net force that is not zero to cause our object to change speed or direction. So Newton's first law deals with a term called inertia. So inertia means resistant to. So it's going to resist the following things. So inertia, things with a large amount of inertia, are going to resist a change in motion. So it's harder to get them to move. They're also going to resist a net force. So again, it's going to be harder for an object that has a large amount of inertia to change its speed or direction. So it's going to resist that push or pull. Inertia also means a resistance to changing velocity. So it doesn't like to change its speed. It doesn't like to speed up or slow down. So it wants to keep moving in the same direction with the same speed. And lastly, it's going to resist a change in direction. So objects with a large amount of inertia want to continue moving in a straight line. If you think about it, if you're in a car and you're turning around a corner, your body wants to continue traveling in a straight line while the car is turning. And so you lean to the left or you lean to the right. So you have a larger amount of inertia compared to other objects. So it's harder for you to change your direction. So you feel that pull on your body as you're making a turn. So you can kind of think of inertia as being equal to mass. So objects with a large amount of inertia always have a larger amount of mass. So bigger masses are going to have more inertia. So like a gorilla. If we compare that to a hamster, which has a very small mass, it's going to have less inertia. So it's harder to get a larger object to change its speed, to change its direction. It's easier to get a smaller mass to change its speed and change its direction because it has less inertia. So answer question 3, which has more inertia? And the answer is the gorilla. So gorilla has more mass and thus it has more inertia. So answer question 4, which will be harder to accelerate? So the object with more inertia is going to be harder to accelerate, so to get it to speed up or slow down. Which can we accelerate easily? Answer is the hamster. So smaller masses change their motion easier. So you just have to remember inertia is the resistance to changing in motion. So large masses resist a net force, they don't accelerate as much. Larger masses are also going to resist changing its speed. So they want to go in the same direction, going the same speed. That's what they're designed to do. Things with a large amount of inertia. Okay, so what if we put rockets on each of the creatures? So we're going to give them both a force of 10 newtons. What are we going to see differently about these two objects once the rockets ignite? So a larger mass should move slower than the smaller mass because it has more inertia. So let's see. So smaller masses are going to change their motion easily. Larger masses are going to resist that change in motion, so they're going to go slower. So you can kind of think of inertia as like stubbornness. So get it, larger things with larger inertia are very stubborn. They don't want to change their motion or their direction or their speed. What would that look like? Something like this. So you see the hamster flies right off, easily can change its speed. Gorilla moves a lot slower because it has more inertia. Okay, answer question 5. Which is going to be harder to stop? A heavy freight train or a light passenger train? And the answer should be the heavier freight train. So again, the heavy freight train wants to keep moving in a straight line, going at same speed. So you have to apply a lot more force to get that heavier train to come to a stop. Less force for that lighter passenger train. The larger masses have more inertia. They're going to have more resistance to changing in motion. So now that we've talked about inertia and we kind of understand what inertia is, let's talk about Newton's first law of motion. So Isaac Newton was a British scientist. He was able to describe the effects of forces on motion with his 3 laws. So his first law states that an object in motion is going to stay in motion, or an object at rest will stay at rest unless a net force acts upon it. So sometimes this law, instead of called the first law of motion, it's called the law of inertia. So most things are going to want to move in a straight line, moving the same speed at which they are moving, unless you apply a net force to them. Or an object wants to stay at rest, and it's going to stay in that position unless you apply a net force. So if we could get rid of friction in our world, which is the net force that acts on a lot of objects, if we didn't have friction, if we pushed a ball down the road without friction, it should continue going down that road in that straight line forever. But in our world, we do have friction. So that friction applies that net force to eventually stop the ball from rolling. Okay? But if we take out friction, we take out air resistance, stuff like that, an object in motion should stay in motion, an object at rest should stay at rest. So out in outer space, where there's no friction, there's no air resistance because there's no atmosphere, if we throw an object, it should keep moving in that straight line until it bumps into another object or reaches another gravity field. So there's no net force to slow it down. So once you give it a push of 10 newtons and it moves like 2 meters per second, it's going to continue moving 2 meters per second out in outer space. So we can kind of see Newton's theory or law here. So if you have like a wheelbarrow with some leaves in it and a rake sitting on top of it, if you're pushing that wheelbarrow and it strikes a rock, a net force is applied to the wheelbarrow, causing it to stop. But the rake on top has not had a net force applied to it, so the rake continues moving forward. So we have to remember Newton's first law. An object at rest is going to stay at rest unless acted upon by a net force. And inertia also says that if we have an object in motion, it's going to stay in motion in a straight line unless a net force is acted on it. So we can apply this to Newton's first law to car crashes. So if we're talking about a car crash and the importance of wearing a seatbelt, when you're traveling down the road at, let's say, 50 kilometers per hour or 50 miles per hour, and you collide head on with something solid, the car slows down and stops within about 0.1 seconds, so a very small time period. But you got to remember, your body is also moving at 50 kilometers per hour or 50 miles per hour down the road with the car. And so if you're not tethered or belted into your car, what's going to happen to you is what happened to the rake and the wheelbarrow. So the force gets applied to the vehicle, but not to you. And so you move forward, and a lot of times you see people get thrown through their windshield. So that seatbelt is what keeps you tied down to the car and allows you to stop with the car. Somewhat safer than not wearing that seatbelt.